Hi, welcome to a webinar on flywheel training. My name is Coach Carmen Bott. Today, I'm just going to briefly summarize an article that was published in Sports Medicine in December 2023 about the best practices in flywheel use. Flywheel methods have been around for quite a long time, in fact, over 100 years. However, we really have only been using modern flywheel systems like the one you see in this image for about 10 years. And most of the research that has been summarized is really only evident in the last 5 years or so. Now, the interesting thing about flywheel training is it allows for maximal or near maximal voluntary forces. Essentially, the way it works is the athlete must pull or push on a strap. And you sort of see that in the image, that line between that metal device that looks almost like a gear and that round red disc. That's a strap, okay? And it's fixed to the flywheel, which is housed inside that platform. And essentially, when the athlete pulls on that strap, it causes the flywheel to rapidly rotate or spin. Now, once the concentric phase is completed on this movement, the strap rewinds at the top and creates a huge pull on the athlete. And then that athlete has to resist or control the descent back into the bottom position. This potentially allows for a greater application of force, especially during that eccentric action. And maybe it can create a mechanical eccentric overload. But we're going to investigate that a little further today. Now, the cool part about flywheels is they allow for a high level of torque over the entire concentric phase and parts of the eccentric phase. So what does this mean? Well, when we compare what it feels like to be on a flywheel versus to be under a barbell or a kettlebell load, essentially it's like this. In the bottom of a split squat, if I were holding a barbell, that would be the hardest part of the movement. And as I moved upwards, so through the concentric phase of the exercise would actually start to get a little bit easier, wouldn't it? Now with flywheels, that doesn't really happen. We've got this constant stress on the muscles and on the body throughout the entire concentric phase, as well as parts of the eccentric phase. So flywheels allow for maximal or near maximal activation during the workout. You really can't hide from a flywheel. It means those muscles will be turned on through that entire range of motion. And because of that, flywheel training may elicit an upregulation of satellite cell activity and transcriptional pathways, especially in fast twitch fibers, which are the sleepy guys, those high threshold motor units that are hard to hit. This increases protein synthesis and incurs hypertrophy. Now, flywheel training may actually generate faster adaptations in strength and power than traditional resistance training. Now, you can take this claim with a grain of salt, and the reason why is a lot of the research in the last 5 years has been done on rehab populations that haven't been overly active or just healthy adults. So if you're trying to apply this to the elite athlete, it may not apply. Flywheel training is also a valid and a very safe way to resistance train because it boasts all kinds of benefits. So what's going to be presented over the next few slides is the recent consensus on its use. So you might be wondering, well, what is the consensus? Well, first, I'll start by saying that flywheel training is actually not a true eccentric overload. Now, there's no doubt about it, there's a massive eccentric stress, and the eccentric stress is very fast. Okay, so we can give it that. However, let's define eccentric overload. Essentially, it's a higher mechanical output during the eccentric phase as compared to the concentric phase, which doesn't really happen because we're using the same load. So eccentric to concentric ratio needs to be greater than 1 for it to be considered a true eccentric overload. So instead, we should just call it flywheel resistance training. Now, if we want to have reliable outputs of flywheel training, it's dependent on the user and it's dependent on their effort. They have to be working very hard. And that takes a bit of practice. We'll get to that next. It also depends on their training background. So, people that have a training background where they've been used to pushing themselves are definitely going to be working a lot harder. So, training age and training background does play a role. The other aspect that affects the output of the training is the moment of inertia that's detected. And so essentially, this is a measurement of load in flywheel training that we'll get to on the next slide. So, in order to obtain the best training response, users must also be coached, and they need to be coached to produce near maximal effort. When we have aspects like the manipulation of the user's technique, their braking strategies, the joint angles and depth that they break at, and the mechanical variables monitored, well, they all play a role in the determination of the presence of a quote unquote overload. Now, the torque or rotational force that's required to achieve acceleration, so the up phase, or deceleration, the down phase or eccentric phase of the flywheel, this increases proportionally to the flywheel overall moment of inertia. And again, you might be wondering what this is. Well, the moment of inertia can be increased or it can be decreased by changing the discs on the wheel. So I want you to have a look at this yellow image. It says Exerfly on it. That's the brand of the flywheel that I use. And the inertia is reading at 0.025 kilograms per meter squared. And so that's a way of expressing load in flywheel training. Now we know how to express load. Well, how do we monitor the outcome of this training? Like whether or not an individual is essentially adapting and improving performance. Well, we want to look at power. Now, power is the main outcome measured variable used, not torque, because the radius on each flywheel can vary, as well as the strap length and the height and length of the user. So it's best practice to record power values from the flywheel to monitor progress. Also, we can't use %1RM to prescribe load on a flywheel, and practitioners should be encouraged to use peak power, mean power, velocity, and force to program and monitor performance. These are all suggestions that came to the surface after reading the Beto article in Sports Medicine. An important aspect of flywheel training is that it requires a familiarization period. Essentially, all training interventions do, because if somebody's never done them before, of course, they're going to need to get used to what it feels like. So spend one, maybe even 2 or 3 sessions getting your clients used to this feeling, because it's a lot different than a barbell or any other isotonic exercise. Now, currently, there's really no evidence-based recommendations to assist with long-term programming using flywheel technology. There are suggestions for hypertrophy, and the suggestion is using moments of inertia around 0.05 for males, and for females around 0.025 upwards of 0.14. But there's no set or rep schemes that are available currently in the literature. To improve strength, well, it seems that volumes need to be similar to what they would be doing barbell work. So for example, if you had a more trained individual, they're probably going to require more sets in order to keep getting stronger. Some suggested moment of inertia loads were roughly from 0.05 to 0.11, and there wasn't really much information on who that was for. Most research that has been conducted has been done, as I said earlier, on healthy populations. And that's been done on mostly power as an outcome variable. So an issue of relevance does persist when we're talking about the athlete population. What I think I find most interesting is the research and the possibility that flywheel training is showing promise in improving change of direction performance in elite athlete populations. Now, practitioners might use flywheel training to improve the braking and accelerating actions that athletes experience. Another key nugget is regarding injury prevention, or probably a better term would be risk mitigation, but the article did say prevention. They suggested using 1 to 2 flywheel exercises at moments of inertia from 0.05 to 0.145. And they suggested that might reduce lower limb injuries, yet much more work needs to be done here. So you might be curious if I endorse flywheel training. Anecdotally, I would say I absolutely do. I bought a flywheel in 2020 and it has been, I don't want to say a game changer because we haven't measured enough variables yet, but it's definitely got some perks. One of the really interesting parts of flywheel training is that it doesn't make athletes very sore or sore at all. And I think one of the reasons behind that is because we don't have a sudden braking phase on the eccentric side. The eccentric side is aggressive, but it doesn't come on suddenly like it does with a barbell. One other thing that the research didn't talk about, which I thought was a bit strange, was that with flywheel training, you almost need about 4 or 5 warm-up reps within the set itself. So essentially, you can't really get on the flywheel and start drumming up high power scores on your first 1 or 2 reps. You need 2, 3, 4, maybe even 5 reps to sort of get things going. And then you might do another 5 or 6 working reps. So it would be really interesting to hear what other people are doing with their mini warm up to their working reps in a set. That's my opinion today, and I do think flywheel training is going to change the game with change of direction performance and injury risk mitigation.